Welcome back. Good morning. Good afternoon. I don't know, it's morning here. You guys took a test though, so actually it's probably 1 p.m. Anyway, I hope the test was good. I hope you did well on it. I know you did well on it. Let's just fix that. I know you did well on it. All you guys are super smart. Unfortunately though, we have to have class after the test. So, first thing we're going to talk about are discrete probability distributions. What these do, they help analyze business practices, business decisions, business solutions, okay? We can establish a probability model, is what it's called. We can assign a probability to a random outcome in a random experiment, okay? That's what these deal with. They deal with random outcomes and with random experiments, okay? So that's what these business model or probability models help us establish, kind of like how likely is blank how likely is it that this event is going to occur, okay? So first things first, I just have a couple definitions I want to give you guys so that way you can understand kind of how we flow into these discrete probability distributions, okay? So obviously if we have a discrete probability distribution, there's going to be a continuous one, but we'll get into that in a future slide. So again, right, a lot of times we denote, this is a capital X, obviously. Normally we denote like general terms as like capital letters, and then we denote like little x with a sub 1 here. This is a sub point, sub 1, x sub 1, our first x value. We usually denote that as like our specific value, okay? So general, specific, okay? So again, discrete random variables, it's just a countable number of distinct values, okay? We can have we can have a clear upper limit of discrete random variables, i.e. class absences in this class. It's a small class. I can easily count up the number of absences here in this class. Or you could have a not so clear limit, okay? Number of text messages in an hour. I don't know how many text messages you can get in an hour. Here's the thing. Some hours you can get 100, some hours you can get 400. If you're getting 400, stop texting. First off, just call. But there's just no defined limit as to how many how many text messages you can get in an hour. It could be a huge amount, small amount. There's no limit to it, okay? So that's what I mean by that. Again, for example, I just give you an example. Here's a decision problem, late morning, 9 to 12, right? Work shift, Adidas, right? We all love Adidas. I'm an Adidas guy. Grew up rocking Adidas. I know there's some Nike people in here. That's okay. Again, they probably have an order processing center. They take a lot of phone calls, and they can handle up to 15 orders per minute, okay? What's the probability that more than 15 orders will arrive in a given minute, right? So this is basically saying, what's the probability that more than 15 calls will come in that minute, and that person will have to get put on hold probably and wait for the next available representative, because I know we've heard that plenty of times in our life, right? So the way we describe this discrete random variable would be the number of phone calls that arrive in a given minute at the Adidas order processing center. And it could be X, again, big X, is equal to 0, 1, 2, blah, 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 however many calls come in, okay? That's how we would define this discrete random variable for this decision problem, all right? So, again, it just assigns a probability to each value of a discrete random variable, right? So we assign a probability to x1, assign a probability to x2, and so on and so forth for all of our outcomes or events in that random variable, okay? So, some rules to follow. The probability of xi, so this is just any x value, right? Xi is any individual x value, okay? The probability has to be between the interval of 0 and 1, right? We don't have a probability greater than 1, but I think we've talked about this before in the last video with probability. Okay, same thing here, right? Has to be between the interval of 0 and 1, and then the sum of all probabilities in your discrete random variable has to equal 1, right? Again, probability sum to 1, same thing for discrete random variables, okay? And again, we also have to follow the rule of functions. We've all taken math classes. I hope we know the rules of functions, right? You can have more than one random variable value that's assigned to the same probability, right? So you can have different x values, that's what we can call these, different x values assigned to the same y value, in this case a probability. We can have different x values assigned to the same y value, but we can't have one random variable. So we can't have one x value with two different y values or two different probabilities, right? The vertical line test, we all know that. We've all heard it before, I hope. That's how we define a function. If it passes the vertical line test and there's no multiple points in one given x, then it's a function and we can use it, okay? So just simple parameters, I guess you could say, or rules to follow in doing these discrete probability distributions. So in this case, right, here's kind of an example again for all you visual people out there. Sample space, I just want to look at my sample space is a 6-sided die. The 6 outcomes of a possible dice roll, okay? You got 1, 2, 3, 4, 5, 6, right? And I kind of put it here. Here's the outcome of a die roll. We can have a 1, 2, 3, 4, 5, or 6. Again, the probability we can assign to that, because different, you can have the same probability for different x values, right? That's still valid. That's a valid function, okay? Again, since there's 6 outcomes, the probability of rolling a 1 is 1/6. Same thing for 2, 3, 4, 5, and 6, okay? So that's just kind of how we can look at that in terms of a discrete random variable. Here's another one for you, okay? Here's kind of how it would look. And this is a tree diagram. We're not going to go into tree diagrams. They're helpful in terms of, and I know this is really sloppy, so forgive me, okay? But I couldn't get it to fit. So tree diagrams, we're not going to go over that, but it's another way of helping you visualize probability, help you visualize outcomes or different outcomes, things like that. So, you know, if we flip a coin 4 times, let's say, we can count the number of heads. So our random variable, discrete random variable, would be the number of heads that come out of flipping a coin 4 times, right? So we can, here's our, I think, I don't know, 1, 2, 3, 4, 5, 6, 16, hello. There's 16 right here. That means there's 16 outcomes, 16 possible outcomes for flipping a coin 4 times, okay? And here's all our different outcomes. We have 4 heads, 4 tails, and in between is all the different variations of heads and tails, okay? So what we'd do is we'd take these outcomes, right? So you can either have 0 heads come up on 4 coin flips, 1 head come up on 4 coin flips, 2, 3, or 4, right? Because that's what we're measuring. 4 coin flips, the number of heads, we can either have 0, 1, 2, 3, or 4. So we assign outcomes to them, and then we can assign probabilities based on those outcomes, right? So 1 out of 16, I can get 0, then if I flip a coin, I can get 0 heads 1 time, right? And that's this 4 tails solution, right? There's no heads in this coin flip, okay? So 1 out of 16. Same thing for 1. If I flip a coin 4 times and get 1 head, that outcome can only happen 4 times, right? So let's look at right here. This happens there. It happens there. It happens there. There's 3. I must have missed 1 somewhere, but you get my point, okay? Did I say that one? I don't know. Anyway, you get my point. There's 4 possible outcomes for flipping a coin 4 times and getting 1 head, okay? So 4/16, 1/16, right? And we can divide these 1 by 16, 4 by 16, and that's where we get these probabilities, okay? And I'm not going to go through 2, 3, and 4 because you guys, I hope, get the concept, okay? And then this is our probability distribution, right? 0, 1, 2, 3, 4, the number of outcomes, and then our probabilities based on those outcomes, okay? Again, so we have 2 different probability distributions, right? We can have a PDF or a CDF, right? And so our PDF is our probability distribution function. That's the one we'll kind of deal with the most. But it kind of shows the probability of each x value. So in this case, right, each of our x values, it shows the probability based on that value, right? So 0, this is just a normal PDF. Again, we'll get into normal distributions later in this chapter, but this is just kind of, so at -1, the probability is like, let's say 0.25, okay? It assigns that given point, that given outcome, a certain probability, this given probability, okay? Whereas a CDF, a cumulative distribution function, if, you know, obviously you see the word cumulative, you think sum of, right? You think sum, you think total. So it shows it's kind of a step stool effect, right? So it shows the cumulative sum of probabilities adding from the smallest to the largest x value, right? So you add the probabilities together as these values increase, right? So let's say I want to take the cumulative distribution function of x equal to, or I guess in this case y equal to 30, I would just add up all of these points. So x equal to 25 plus, or I guess the probability of x equals 25 plus the probability of x equals 20, and then so on and so forth all the way down here. We add these up and we get our probability here, right? Just think of it as a step stool, okay? All right, expected value, right? Our expected value of probabilities, it's the sum of all x values weighted by their respective probabilities, right? It's otherwise known, especially in probability, otherwise known as the mean. In this case, though, we did talk about weighted mean, right? In numeric descriptions of variables, right? This is just a weighted mean of probabilities, okay? That's all the expected value is, right? So it's a good measure of center for probability. Obviously a weighted average because outcomes can have different probabilities, right? We usually call it capital E of x, right? Our expected value of x. The mean, again, we use the symbol mu because, you know, we like to keep it consistent. It's a Greek letter. And that's the Greek letter for mean a lot of times. So we'll use the mean for the expected value of probability distribution, okay? The mean formula of probability, right? It's all it is you know, we've taken the sum and then we divide by the number in our sample space. Well, in this case, we just take our x value and then we multiply it by the probability of x. It's really easy, okay? No dividing, nothing like that. We just multiply. And then we take the sum of all those parts, okay? So we have our x value, our p of x, our probability of x, okay? And then we just do 1 times 0.10. Obviously, that's 0.10. And then we do that for all these outcomes. 2 times the probability, 3 times the probability, and then we sum all of them up, and that's our mean, our expected value, I should say, of our probability distribution, okay? Real simple, real easy. And again, we kind of use this expected value, and I just gave you an example here. This is for a life insurance policy. This is how we kind of expect, these are how life insurance companies kind of expect or calculate their payout for their premiums, right? So you have to pay a certain amount every month or every 6 months or so in order to keep your life insurance policy, right? So it's, as you're saying, suppose a life insurance company sells a $120,000 1-year term life insurance policy, right? So if you die, I hope you don't ever die, but at least if I'm still alive, but you get my point. I digress. You get $120,000, okay? Or you don't get it because you're dead, but who, your significant other, your, I don't know, your parents, somebody, okay? And again, they're giving this policy to an 18-year-old female for $150. So that 18-year-old female is going to pay $150 for this $120,000 life insurance policy. That's not bad, okay? It's not bad at all. Of course, they assign a probability to that, right? The probability that the female survives the year is pretty high, right? It's almost a full 1. It's almost a full 100%, full 1, okay? 0.999356. She's pretty smart with how she lives. She doesn't take any risks, it looks like. So it's just asking compute and interpret the expected value of this policy to the insurance company, okay? What's the expected value, right? So we have to have 2 outcomes, right? Our outcome that she survives is obviously the probability of that outcome is 0.99356. And then so obviously we have to find the probability that she may die, okay? Unfortunately. Again, that's just gonna be 1 minus the probability that she survives. So this is the probability that she dies, right? And of course, we have to assign an outcome to these x values. So again, I'm not going to go into all of this, but you get my point here. The outcome that she survives is $150. She has to pay the insurance company $150, right? It's not free. So we assign the probability the x value 150. That's where she survives, right? And obviously our probability of that event happening was given here. And then we found this probability. And then if she dies, the insurance company has to pay out $119,850. Okay, this is just the 120 minus 150, right? That's how they got that. So these are our 2 outcomes, okay? And then if we wanted to find the mean or expected value, we would just, do this formula here. The sum of the x outcome times the probability of the x outcome, okay? So in this case, we do 150 times 0.99356, we get $149.90. And then we do this times this, you get negative 77.18. We sum it, or we take, I guess, add it all together, we get $72.72, right? So the insurance company expects to make an average profit of $72.72 on every 18-year-old female it insures for 1 year, okay? Which, depending on how big the insurance company is, $72.72 could be quite a chunk of change. You know, if you insure like 10,000 18-year-old girls, okay? Or females, you know, they're women. So anyway, this is just something that you can use. This is just a real life example of that kind of use of expected value, okay? Again, talked about variance and standard deviation. We know this, okay? Follows the same principle and formula as a regular variance of a sample, but again, it's weighted due to the probabilities, okay? Again, variance and standard deviation, they deal with measures of variability. We denote it, especially in here, as VAR, so VAR, variance of X, but usually, again, we use the sigma squared, okay? Right, sigma squared is variance, sigma, standard deviation, okay? And then the formula for variance is just the sum of X minus the mean squared times the probability. Same formula for variance as the regular probability we talked about last chapter, but you just multiply it by the probability, okay? And then, of course, the standard deviation, you just take the square root of the variance. Really easy, all right? I did this worksheet in Google Sheets. It took me all of 5 minutes. It's really simple, really easy, if you know how to work it and know all the different functions you can use, okay? I just said there's a hotel. They wanted to look at, you know, their mean and their variance of February room rentals and see how distributed their data was given their probabilities, okay? So I just assigned, there's 7, you can either rent 0 rooms, 1 room, 2 rooms, all the way up to 7, okay? And so I just assigned some random probability to it. There's no merit in these. I'm just, you know, I just kind of was goofing around. So again, you just work from the top down, okay, from left to right, and you can kind of just do X times your probability of X, so 0 times 0.05 is 0, go all the way down, and you sum that gets your mean, or your expected value of that probability distribution. You can do X minus your mean, where you get all these values, and then you square that, right? This is what our variance is going to end up being, right? So you square that, and then you multiply by the probability, okay? You get all these values, you sum it, and so our variance will be 4.22. So, and then of course our standard deviation, just the square root of that, okay? Really simple, really easy. I did this all in 5 minutes. You should be able to do that as well. So our mean for this is 4.71 with a standard deviation of 2.055 rooms, okay? So this is the average that the people rent, right? Obviously we can't rent 4.71 rooms, but it's the average, okay? So I guess you could round up to 5 since this is closer to 5 than 4, but you get my point, right? So in this example, right, so our mode is definitely 7, right? If you look at the probability of that happening, the highest probability out of all these is 7, okay? So our deaf people, I don't know, I guess it's a family reunion time, I don't know, but definitely people rent 7 rooms the most, but the average is only 4.71 room rentals, so you know, it's just kind of a weird coincidence. But the variation, or the standard deviation is 2.06, so it has some pretty considerable spread if you look at it, right? Because 4.71 plus 2.06 is all the way over here somewhere, right? And is all the way over here. So we have a pretty good spread around the mean, okay? And it's bimodal. You can see you have 2 peaks here, and you know, you guys can get it, skewed left. So what we're gonna do, should be a pretty small class, so I want you guys to work these out together. Use the book if you have it, and then we'll get back with it after this, okay? See you guys in a second. All right, welcome back. We're gonna go over what are called Bernoulli experiments, right? Famous Italian mathematician, statistician, and basically he was able to come up with an experiment and give probabilities to it. And this is just an experiment that has only 2 outcomes, right? And you can define the outcomes as either a success or a fail. And again, we just denote these X equal to 1 for success, 0 for failure, okay? And A lot of times we denote the probability of success as pi, the Greek letter pi, and this can only be a value between 0 and 1, okay? And this is important because we don't want to confuse this letter pi, right, with the mathematical constant, 3.14159. But you get my point, right? Don't confuse, and especially in statistics, right? There are instances where we have to use pi. Well, I say that. Probably not as likely, but whenever you see this, it's probably dealing with Bernoulli experiments, okay? It's basically just the probability of success, okay? That's all that this is, right? The probability of success is pi equal to point whatever, between 0 and 1, okay? So don't confuse it with the mathematical constant, right? So that means, obviously, if this is the probability of success, the probability of failure is just 1 minus pi. Easy, simple. So probability of success always remains the same for each trial, right? If you have a probability of success, a probability of failure, the probability of success is always the same, okay? Flipping a coin, for example, the probability of success of flipping heads is always 0.5, right? That's easy. No matter how many times you flip it, it's always 0.5, okay? And again, success doesn't always have to mean something good, right? It can mean something undesirable. We'll talk about that. So really, success just means an event of interest, right? Something we want to look at. And just some examples real quick. Flip a coin, right? Our success in this case would be heads, fail, tails. So our probability of success, pi, 0.5. Inspect our jet turbine engine. Again, this is not a desirable outcome. If there's a crack found, that's a success. That's not a success in terms of, jet turbine engines, but that's what we're studying, okay? Fail would be no crack found, which is hopefully what we want, right? So our probability of success is 0.001, right? That's kind of a defect rate. We want our defect rate to be as low as possible, okay? So in this case, this would be an undesirable success. Purchase a tank of gas, right? We do that at least once a week, if you drive a huge truck, or, if you drive a Prius once a month. 1, chance of probability of success, 1, pay by credit card, what we want to study. 0, do not pay by credit card, okay? Probability of success, 0.78. I always pay with a debit card or a credit card, so anyway. Or if you do an allergy test, right? 1 is a positive test, 0 is a negative test, and then our probability of success is 0.004, okay? You could be allergic to dairy or something, you give an allergy, or you take an allergy test, see if you're allergic to dairy. Probability of success of you being allergic to dairy is 0.004, okay? That's what that means. Okay, I put this slide on here, and I did it late because I wasn't sure how to, think about what I wanted to say, but I just put this table in here to show you that that value pi is just it just depends on the situation, right? It doesn't always have to be the same, it doesn't always have to be different, it can be the same, but it just depends on the situation, okay? That's why I put those examples up there. And the definitions of success and failure, we could easily they're arbitrary, right? So they can be switched and flip-flopped however you want. In this case, right, if you could switch these, right, and 1 would be no crack found, which would be a success, and 0 would be crack found, you would just flip the pi value, right? So then our probability of success would be 0.999, okay? That's what that means, all right? Again, and usually we define success as the less likely outcomes, so that pi is less than 0.5. I don't know why, that's what they like to do. I assume it helps with getting more accurate probabilities. That's what I assume. So our Bernoulli mean and variance, it's actually a lot easier to get the mean and variance of a Bernoulli experiment, than a probability distribution. I want to say Bernardi experiment so bad. Anyway, but so the expected value of a Bernoulli experiment is just pi. It's just our chance of success. That's our mean, or our expected value of a Bernoulli experiment. Okay, really easy. That's great. I don't have to do any calculation. You kidding me? Fantastic. So our variance is literally just the chance of success times the chance of failure. Okay, that's all the variance is. Pretty simple stuff. And these are just like the This is just the formulas for kind of how they get here algebraically. We're not gonna make you do that, talk about it, describe it, anything like that, but it's just good to see. I don't know, I like numbers, I like statistics. I put it on there because I liked it, okay? So, know this, right? It's really easy for Bernoulli experiments to get the mean and variance, all right? So in a binomial distribution, again, binomial distribution, this is just a Bernoulli experiment repeated n number of times, okay? Again, flip a coin, we do it 4 times. The binomial distribution would be a Bernoulli experiment repeated 4 times, okay? So again, we're interested in x, right? That's our random variable, and our random variable for binomial distribution is always the number of successes in the trial, okay? So the binomial random variable x is the sum of n independent Bernoulli random variables, right? That's just exactly what I said. All these are just the number of successes in your however many trials you did, right? So if you did 50 trials and you got 24 successes, every random the random variable would be all 24 successes. That's what that's saying, okay? Again, binomial mean and binomial variance are all super easy. Binomial mean, you just take your number of samples or number of your trials, number of times you repeated the Bernoulli experiment, and you multiply it by the chance of success, right? So if I did 30 coin flips, my chance of success is 0.5. I'll just do 30 times 0.5. That's the mean of a binomial distribution, okay? Binomial variance, you do the same thing for Bernoulli experiment, right? Pi, chance of success times the chance of failure, except again, you just multiply it by the number of times you did the experiment, okay? So 30 times, right, times 0.5, again, 1 minus 0.5 is 0.5, so 30 times 0.5 times 0.5, just for, I'm just giving you an example, okay? It's not always going to be 30, it's not always going to be 0.5. Standard deviation is just the square root of the variance, okay? That's all that is. This looks scary, I know, but it's going to be fine. Okay, so binomial probability of a particular number of successes, again, probability of x equal to x, right? So probability of x equals a certain successful outcome, right, is determined by the 2 parameters n, which is our number of trials, and our chance of success, pi, okay? So the binomial probability function is n, this is an exclamation point, like, oh, is he screaming the number of times? No. N exclamation point, it just means n factorial, okay? N factorial is kind of just like let's say I have 7 factorial, right? Let's say the number of times I completed the experiment was 7 times. 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1, okay? Not times 0. We don't include 0 because anything times 0 is 0, right? That's why we don't include it. So, n factorial is just like the progression of numbers till you get to 1. That's what n factorial means, right? So this is an ugly function. It's definitely cumbersome, okay? And then x, of course, is our outcome, right? So whatever we put here. And then obviously we just substitute all these numbers in for these variables, right? N is the number of times we completed it minus x. So 7, let's say we want to look at outcome number 2. So we have 7 factorial here, 2 factorial, 7 minus 2 factorial, right? So 5 factorial, okay? And then we look at our chance of success to the x power, so 2, so pi squared times 1 minus pi n minus x, right? So 7 minus 2, 5, okay? And again, I think I have an example on the next page for you to look at. I even put the Excel binomial distribution function for you, okay? So all we have to do to find the binomial distribution of our data in Google or Google Sheets or Excel, all we have to do is hit equal binom.dist, distribution, binomial distribution, right? And then we put our x, so our outcome we want to see. In this case, if we want to do 2, we would do 2. Our number of times we did the experiment, 7, right? Chance of success, 0.5, and then cumulative. So what I mean by cumulative, so we can either do one of 2 things. Cumulative can either be 0, and that's if you want a probability distribution function, right? Just the regular PDF that we talked about. Or you could do 1, and that's if you want a cumulative distribution function, right? A lot of times we'll do 0 for PDFs, right? We'll do 0 more than we'll probably do 1, okay? That's just for Excel though, right? And so, oh gosh, again, sorry that this is so blurry, but you can it's not that blurry here in person. So, but anyway, These are just example formulas for you guys to follow. Like let's say I have 3 outcomes, 0, 1, 2. Okay, this is just a number of successes again in the thing. It's not like again in a Bernoulli experiment we have outcome 1 or outcome 0. This is just the chance of the probability of success for that certain successful outcome in a Bernoulli experiment. Okay. And again, if I want to clarify 0 factorial here, you're like, oh, what the heck is 0 factorial? Wouldn't that just be 0? No, 0 factorial is actually equal to 1. Don't let that confuse you, okay? 0 factorial is equal to 1, right? Okay, so this is just like plug and play. You have 2 factorial here over 0 factorial, 2 minus 0 factorial, 0.5 to the 0 power. Anything to the 0 power is always 1, 2. Don't forget that. 1, not 1, 2. Okay, I meant 1 also. And then again, you have your 1 minus 0.5. I think these are actually coin flips if you don't, because you have a 0.5 chance of success here. I would just assume that in this context, it would be a coin flip. So again, we have 2 times 1, right? 2 factorial is 2 times 1. So 2 over 1 times 2 factorial, which is again 2. So 2 over 2, we have 0.5 to the 0 power is 1. 0.5 squared is 0.25, 2 over 2, and then we multiply all these together, we get 0.25, okay? This is just examples, right? I want you guys to get familiar with this, so that way you can just crank these out on your calculator if you'd like. I'm pretty sure your calculator also has a binomial distribution calculation that you're able to calculate, but if you can't find it, it's been a while since I've used a calculator like that, so I don't honestly remember if there is one. If you can't find it though, you can easily just plug in these numbers and get your binomial distribution probability. Okay. Again, like I said, this formula can be heavy and cumbersome even for a small sample size or small sample. We can use Excel to find it quickly, but when taking a test, Excel isn't always handy, obviously, because I'm not going to let you use Excel on a test. Sorry, guys. But Appendix A can come into handy to look up binomial probabilities for selected values of n and pi. Again, I even put the pages you can find in your textbook. If you don't have the textbook, what we're going to do is we should have made copies of all these tables in the back of the textbook, and we'll give them to you. On final day, when you take the final, we'll give these appendices to you, okay, at no charge, okay? So you'll have these on the test. If you don't have the textbook, don't worry about it, okay? And we'll give these to you before the test too, so that way when you work problems and practice, you have these to look at, okay? I just put this. There may or may not be a manual and an easy calculation problem on the test, right? So I may tell you, hey, manually calculate this binomial probability. I may ask you to manually do it, okay? So that's why you need to know the formula, all right? But there may also be an easy calculation problem on there where you use the Appendix A. Study both, okay? And again, I have the textbook here in front of me. The table just kind of looks like this, if you can see it. It's a really big table, right? So you have your number of, goodness gracious, sorry guys. You have your number of trials here, 6, 7, 8, 9, goes all the way up to 10, 11, 12, 14, 16, right? And then we find our outcome, right? And then this is just our pi, right? Our chances of success, okay? And if you have any questions, I know this is really small and the video doesn't do it justice. Mrs. Bernardi can help you guys out when reading the table because she has the textbook as well, okay? And she can help you guys kind of read it and go over it, okay? So that's how we can kind of calculate binomial distributions, okay? Binomial probabilities. Again, we can use binomial probabilities to classify shape of the data, okay? And we do that by looking at the value of pi, right? The chance of success, okay? So if the chance of success is less than 0.5, again, it's a skewed right data, okay? That means it's skewed to the right, it has a right tail, okay? If the chance of success is equal to 0.5, it's symmetric, right? We have that nice little bell-shaped curve. And if it's greater than 0.5, it's skewed left, okay? This is just, it's good to know. I just thought it was interesting, okay? All right, now we're gonna get into what's called a compound event, all right? And compound events are just binomial distributions. They kind of add on, like they're written usually in inequalities, right? So like, let's say I want to find the probability of a binomial distribution where x, the outcome x, is less than or equal to 2, right? So in this case, I would have to find the binomial binomial probability of the probability of x equal to 0 plus the probability of x equal to 1 plus the probability of x equal to 2. This is where that appendix might come in handy, and I don't have to calculate all those three by hand, right? That's where that would come into handy, right? So if it was just 1, if I was just asking you to do probability of x equal to 2, that's easy. Do it once, you're done, you find the probability, right? But in this case, it's 3 different ones, and sometimes you can get up to, 15, 16. That's where that appendix would come in handy, okay? In Excel, this is, again, I just put a formula in here for you guys to kind of see it. Again, it's always good to check your math, check your work, and you can put it in Excel. And if the Excel is approximately the same value as yours, because again, there's rounding errors in there, you probably did the binomial probabilities correctly. So again, we did 0 cumulative for the anytime it's x equal to 2, right? We can do the 0 at the end of the formula. But in this case, if it's inequality like this, we want it to sum to 1, right? That's our CDF. Because we have to sum these together, we have to do put a 1 at the end, okay? And again, to interpret phrases such as more than, at most, at least, right? You're going to see a lot of these in statistics, so it's good to know these kind of phrases so you can kind of interpret what it's asking for, okay? And again, there's a figure in your textbook. I couldn't get it on here. There's not enough time for me, I apologize. But if you don't have a textbook, Mrs. Bernardi can kind of show you guys what it kind of looks like, and y'all can talk about it, okay? It's in chapter 6. But this is what compound events are, right? Just an event added on to another event, added on to another event. What's the probability of all those events happening? So how do we recognize binomial applications, right? How do I know if this is a binomial distribution or not? Well, here's 5 main ways you can classify if it's a binomial distribution or not, right? First, is there a fixed number of trials? If there are, great. You made your first sign. Are there only 2 outcomes for each trial, success or failure? Again, huge thing. Probability of success for each trial pi remains constant. So if the chance of success is always the same, 3 out of the 5, you're looking pretty good, okay? If the trials are independent of each other, right? Success or fail, they have no dependency on one another, okay? Random variable x is the number of successes, right? If your random variable is all of the successes, you've met the criteria. You can probably use binomial applications for this, okay? And again, that's where we do all the pi times n times pi times 1 minus pi, all that stuff, mean variance, all that, okay? All right, so we're gonna pause right now. I want you guys to work some of these problems out, and how about this? I said you can use Appendix A for 6.23. How about you can use Appendix A for 6.23 and any of these problems that have inequalities. So anything that deals with an inequality, you guys can use Appendix A, okay? So that's what I want you guys to do right now, and we'll see you guys after you're done. Okay, we've talked about discrete probability distributions. Now we're going to talk about continuous, okay? Again, I'm just going to review. Discrete random variables generally deal with counting something. Continuous random variables deal with measuring something, okay? Measuring something on an interval, right? We can't have a non-integer decimal value for continuous probability again, right? We've talked about the difference between discrete values and continuous values, kind of the same general concept in terms of probability distributions, okay? So discrete random variables defined at a point, probability of x equal to 3, which is the outcome, or a sum of points, right? X less than 3, just all these added up. And a continuous variable, it kind of doesn't make sense to kind of think about probability, especially in a continuous distribution, of thinking of it at a particular x value, right? Because they're not discrete, because they're continuous, they can be decimal values. It doesn't make sense for them to be thought of as set at a particular given value, okay? We don't assign probabilities for those specific values, right? Rather, we define them as what's called an area under a curve, area under the curve, using the probability distribution function we talked about earlier, PDF, okay? Again, I said it up here, but it's defined on intervals, right? So what's the probability of what's the probability of x being between 53.5 and 54.5, right? That's that interval that I'm talking about. And just for you guys to kind of see it visually, right? Discrete values, event 1, event 2, 3, 4, 5, 6. We assign probabilities to these based on, the event. Or in a continuous probability distribution, we think of it as a smooth line, right? A smooth function. Again, this passes the vertical line test, okay? We guys see that, I hope. But think of continuous kind of as like a line, okay? That's how you can kind of differentiate between the two. So we talked about area under the curve in 2 slides ago, okay? We're gonna really focus on it in this little section, okay? So again, we don't want to talk about continuous probabilities in terms of the sums of those probabilities, right? We want to think about them in terms of area under the curve, okay? So in calculus terms, excuse me, got an eye itch. In calculus terms, you're gonna learn some calculus today. Who knew? You're welcome. We kind of say that the probability from the value A to the value B is the integral, right? And all an integral is just an antiderivative of a function. You don't have to learn that. I promise it's going to be fine. You don't have to take any integrals today, any derivatives. But if you take calculus, you'll learn what these are, and they're super fun. They're super cool. Okay, it's basically just the tangent of a line at a given point in a function. Again, not that important to you. You'll never have to do that unless you take calculus. But it's interesting to me. I love it. But anyway, that's all that this is saying. Area under the curve. We take the integral of the probability density function f of x, so whatever the function of the curve is, we take the probability function of that over the interval from a to b, okay? Again, this is just the mathematical side of it. You will never have to do this, but it's interesting to learn about and know, and I put it in here because it's important, okay? So, again, because the probability of any given point on that line is going to be equal to 0 because it's a continuous function. We don't have discrete variables in there. We can kind of classify this, right? This inequality, it's going to be the same as this inequality, okay? So anytime you see this, it's the same as this in a continuous function, continuous probability function, excuse me. So this right here, you don't really have to differentiate between less than or less than or equal to, okay? They're the same thing in a continuous probability function, right? So anytime that way it's not as confusing if you're like, oh, well, he said less than, but then he's including the numbers in the interval. It's because they're the same in a continuous probability distribution function, okay? Again, we'll never have to calculate continuous random variables and their means or their variances because, let's face it, you have to take an integral. And we haven't learned that, and you won't learn it unless you take calculus, okay? So we're not going to do any of that, but it's good to know that it's the same formula as the mean of discrete random variables. We just replace the summation with the integral sign, okay? This little loop-de weird thing is the integral symbol, okay? So yeah, that's all that means. I wanted to give that to you so you can look at it, okay? So that's what continuous probability distributions are. Now we're going to get into what's called normal distributions, right? And we've already mentioned this several times in previous chapters. Mentioned it several times in the last couple slides. But it's often denoted as a capital N parentheses with the mean and standard deviation, right? So that means that any given distribution with mean blank and standard deviation blank. And if you denote it in here, that means it's a normal distribution, right? And so we talked about normal distributions, right? You can have an interval, so mean minus 3 standard deviations away, mean plus 3 standard deviations away, includes almost all the area under the curve, right? We learned that based on the empirical rule. So we learned that in chapter 4, right? The empirical rule. Besides mean and standard deviation, again, normal probability density function f of x depends on E, which is again a mathematical constant there. gave you the value and pi. This is actually the mathematical constant pi, not the chance of success, but the actual mathematical constant. Again, we won't ever have to take any of these calculations for yourself because it deals with integrals, but I'm just giving you some context, some background knowledge, so that way when we get into it, you can kind of understand where these probabilities come from, okay? Again, expected value is always mean and variance is sigma squared, okay? And normal distributions, always symmetric. That's important, okay? You think of the symmetric as that nice bell-shaped curve, right? Mound-shaped or bell-shaped, right? We have our normal distribution here. And again, they all have similar shape. They all have same shape. The only difference is their scale, right? If you look here, 0, 2, 4, 6, 0, 5, 10, 15, they're the same shape. They just have a different scale, okay? That's the only thing different about normal distributions, all right? But think about it in terms of, you know, a bell or a mound or a hill or something like that. Okay, so what is normal, right? You can find them a lot in engineering, science applications. Just for you guys asking, where would you find these? You find them economic and financial data, analysis, stuff like that. Behavioral measurement scales, marketing research, operations analysis, all that stuff, guys. They use normal distributions for their data, okay, and how to analyze it, all right? Again, it's really especially important for hypothesis testing. So if I want to test out a hypothesis that I have, normal distributions is a good way to do that, okay? Or probability, normal distributions dealing with probability is a good way to kind of do that. Again, things to look for in terms of normal distributions, right? Be measured on a continuous scale, has to be continuous, okay? It has to possess a clear center, right? It can only have one peak, so unimodal, right? We talked about bimodal, all that stuff, right? Has to be unimodal, so one peak, and then it kind of has to have exhibiting tapering tails, right? So if we have your one peak here, it has to have tails on either side and be symmetric about the mean, where it has so equal tails, right? So it has to have tails and they're equal. That's really, I mean, pretty self-explanatory, but that's kind of what you look for when you look for normal distributions. Again, we have our standard normal distribution. Again, since there's different normal distributions for every pair of values of, you know, whether any kind of mean or standard deviation, we can again transform these variables by subtracting the x value, or by subtracting the mean from our x value and then dividing that by the standard deviation. Again, we talked about this in chapter 4, I believe, when it came to z-scores. Same thing here, right? This is just our z-score. And so with our mean and our standard deviation, of course, right, we just standardize the variable, right? Since these can be any kind of different variable or different distribution, we can standardize it by giving it a z-score. How far away that is, or that value is from the mean, right? We talked about that in chapter 3. Chapter 4, excuse me. But again, we're talking about a population distribution set of sample data because this has to do with probability. Again, the integrals are a key part of how they find these. Since we don't take integrals in this class, they've worked it all out for you. So if you trust all the statisticians that did this for you, it's great. And so there's these, what's called an appendix C-1, and it's in the back of the book here. Again, we'll give these tables to you to work these problems out. We'll give them to you on the test when you take them, so that way you don't have to, like, you know, take an integral on the final. But they're prepared so you can so you can look up any desired normal area that you want. Okay, and there's appendix C-1 and there's appendix C-2. Okay, and it's important to know which one goes with which. Okay, so it actually tells you in the appendix that appendix C-1 shows area from 0, which is the mean, right? So from 0 to z, so from the mean to whatever z value you're looking for, right? It's a middle area, okay? And it goes using increments of 0.01, so you can do from z 0 to 3.69, I think is the max number that it goes to, because beyond this range, the areas are too small to calculate, or not that important to calculate, okay? So it goes only to 3.69. And so I just kind of put a couple examples here so you can kind of look at them. if we wanted to find the probability of the z, or the probability of an event happening where a z is between 0 and 1.96, again, we would select a row. We'd go to our appendix C-1 back in, I think this is page 767 of your textbook. You'd find the row of your z-score 1.9, right? There's a row here. It's about middle, halfway down appendix C1. And then you can select the column up top of 0.06. Because again, 1.96, you do 1.9, you find your 1.9, and then you look up top to find your 0.06, and that gives you your z-score, okay? 1.96. All right, and then you find where they intersect, and that's your probability, all right? And so if you do that based on the table, this probability is 0.4750, all right? Or you can think of this as your probability is 0.4750, or you can say this interval covers 47.5% of the curve. That's what with one or the other, okay? And so that's what this probability is. Or we can find a right tail area, right? So if I wanted to, instead of looking at this interval, I can find the probability of z being greater than 1.96, right? And so all I would do is think about a normal bell-shaped curve, right? The mean is right in the middle. So in this case, 50% of the data is to the, 50% of the data is to the right, and 50% of the data is to the left. So if I wanted to find everything from 1.96, I could just find everything, I could just do this interval and then subtract it by 0.5. And that way I don't have to deal with the whole bell curve, right? I can just deal with the half that I'm looking at, okay? It's easier to deal with, easier to look at. Instead of trying to figure it out based on the whole curve, I can just figure it out just due to the right, because the z-score is on the right, right? That's just one way to look at it, okay? And so you just do 0.5 minus 0.475, and you get 0.0250. So that's the percentage. So 2.5% of data is to the right of 1.96 on your bell curve. Yeah, I hope that made sense, but it'll make more sense as you do more problems and get a feel for how this table works, how your bell curve kind of formats itself and all that stuff. So we can also find the middle area, right? I gave you plenty of examples to look at, so you can look at all these, but you find a middle area. So for probability of z, or negative 1.96 to 1.96, right? What's the area under that curve? From that z-score, from z-score negative 1.96 to z-score 1.96, right? But because it's a normal distribution, right, it has equal tails, it's symmetric, we know that the probability of negative 1.96 to 0 should be the same as the one we figured in this last slide here, from 0 to 1.96, right? If it's symmetric, that should be true, right? That just makes sense logically. So this probability is the same as the other one, right? If we go from 0 to positive 1.96, they should be the same. And so adding these together, we get 0.4750 plus 0.750, we get 95. So that means 95% of the data is enclosed between this z-score and this z-score. That's a lot of data, okay? And again, that deals with normal curves, just normal curves. Appendix C-2, right? This is the second part of the appendix. This shows the cumulative normal areas from everything to the left of z, right? So everything to the left of your z-score, that's what it's going to calculate for you, okay? So if my z-score is positive, like 1.96, it's going to calculate everything from 1.96 all the way to the left-hand side of your data, okay? There's no like stopping point here. It doesn't stop at 0. It just keeps going all the way to the end of your data, okay? So using this approach, again, the cool thing about these appendices is you can use either one of them, right? You just have to make sure you use them correctly in order to find your area under the curve, all right? And you can kind of like, I kind of put a little cheat sheet here as to when it's easier to use either of the tables, right? But in this approach, we can kind of see like the probability of z being less than negative 1.96, again, if we calculated it on one side, it should be the same on the other side, right? Because they're normal. So we calculated z greater than, here we go. We calculated z greater than 1.96, right? On this one, we got 0.0250. So that means on the flip side, if z is less than negative 1.96, it should be the same probability, right? Yeah, this one, okay? And then so the probability of z being less than positive 1.96, we could just do 1 minus this, right? That makes sense, right? Since this is less than negative 1 and this is less than... Anyway, you could easily calculate this finding the appendix in, I don't know what the correct way to pronounce it is. I just like appendix better. Anyway, you can calculate this using C-2 because it's everything to the left. This is everything to the left of negative 1.96. This is everything to the left of 1.96. Okay, I missed a but there. Subtraction, we get, like this one here, we could do the probability of z less than 1.96 minus the probability of z less than negative 1.96, and we get the same exact value, right? It's just a matter of which is easiest to you, right? You can use C-2 to get the same exact value for this one, or you could use C-1 to get this exact same value, right? Whichever is easiest. But both tables can use the same results, but use whichever is easier for the area you're trying to find, right? So C-1, it's often easier for middle areas, right? So in this case, C-1 would be easier to find this one, right? It's a middle area between two z values. Basically, all you have to do is find the z value from 0 to whatever z value or z score you're trying to find, and then you multiply it by 2 because, at least if they're the same, that is. If they're not the same, then you can't do that. But if they're the same, like this one, you find one of them, you multiply it by 2, you get both of them, okay? Or you get this number, okay? C-2 is often easier for left-out areas and some more complex areas, right? I don't know how complex we'll get in this class, but they can arise, and a lot of times C-2 is easier for that, right? So anything to the left of your z-score, that's what C-2 handles, okay? Again, we can use these appendices to do different things, right? We don't need to just find probabilities, right? We can find a z-score for a given area, right? So we can be given the area, now we just need to find the z-score, all right? So in this case, what z-value defines the top 1% of a normal distribution, right? So the top 1% is everything to the right of 99, right? But in this case, we know half the area lies above the mean, right? So 50% of the data lies to the right of the mean. So let's just use that 50% and make it easier on ourselves, right? So in this case, 49% of the data must lie between 0 and z. That makes sense, right? So searching appendix C-1 for an area of 49.49, right? So we searched the table C-1 to find our percentage, our area under the curve, or the probability, right, of the closest one to 49%, right? And in this case, we find that the z scored 2.33. So if you go to 2.3 and then 0.03 in your data table, you can find that the z-score, the area under the curve is 0.4901. That's the closest we can get to 49%, right? So without interpolation, this is as close as we can get to 49%, right? So as close as we can get, so a lot of times you won't get exactly on it, but as close as we can get, right? That's the z-score we use, okay? Again, we can find other important areas in the same way. Oftentimes a lot of companies are interested in the top 25%, 10%, 5%, 1%, etc. Or you can find middle areas of that as well, right? 50%, the middle 50%, right? So from, however much is 50% of the data between two z-scores, okay? 90%, 95, 99, so forth, all that stuff. Again, this could be convenient for you if you wanted to find the top 25%. It could be convenient to record the z-values that you find and use them for quick reference. That way you don't have to go back to this table every time and look and do all that stuff, right? Because these are standardized values. They should work for all z values, okay? So anyway, that could be good for you. Again, we can find the areas by using standardized variables, right? So let's just say, obviously we had an exam today. Let's say Jarrett took the exam and he made 86 points on it, okay? 86 out of 100, let's say. The class mean was 75, right? Not a bad mean, but could be better, I guess. I'm hoping for a higher mean on this test. But has a standard deviation of 7, right? So you could ask, what percentile is Jared in, right? AKA, what is the probability that X is, what is the probability that X is less than 86, okay? So everything to the left of Jared's score, what percentile is that, right? So first we have to calculate his standardized test, his standardized Z-score. So again, we know the formula for that. Z-score is his score minus the mean divided by the standard deviation. So 86 minus 75, 11, right? Divide that by the standard deviation, which is 7. That's Jared's Z-score. That's how far away he is from the mean. So he's 1.57 standard deviations away from the mean, okay? And again, since this is less than, so that means everything to the left, this is a left tail probability distribution, we can look at Appendix C-2 because that clearly deals with everything to the left of your Z-score, which is an easy find, okay? So we find 1.57 in our appendix, whatever, and we can get the probability, which is the area under the curve, which is 0.9418. So Jared is approximately in the 94th percentile of all test takers that took this statistics exam. So way to go, Jared, you're pretty good. He scored better than 94% of you guys. I don't know if that's true. I hope it is. We don't know. We'll figure that out when the grades come out, I guess. So that's just another way to do it. Another example, right? Let's say on the same exam, right? Mean of 75, standard deviation of 7. What's the probability that a randomly chosen test taker would have a score of at least 65, right? Again, so at least 65, right? That means 65 or greater. Again, so that's what this means. Probability of X being greater than or equal to 65, okay? So we can, first off, step 1, I gave you step-by-step instructions. You're welcome. First thing we do is standardize the data, okay? So we take our score, 65 minus the mean, divide by standard deviation, we get negative 1.43, right? So we can use either of the appendices, C-1 or C-2. If you use one or the other, you have to make sure you use it correctly, okay? And you can use C1, C-1, in this case, would be everything from, or Z greater than or equal to a negative 1.43, so everything to the right, right? So in this case, what we can do is, we can find the probability of negative 1.43 to 0, and then we can add 50% of the data to that. Because again, it's negative 1.43 to 0, and then everything to the right, which is 50% of the data. That's where this 0.5000 comes in, okay? So we find our Z value, or we find our area under the curve for this probability, which is 0.4236. Add it to 5, or add it to 0.5, so that means that 92.36, or I rounded up, so 92.4%. There's a 92.4% chance that a randomly chosen test taker would have a score of at least 65. That's a pretty high percentage. If you use C-2, again, that's everything to the left of the Z-score, right? So in this case, all you'd have to do is do 1 minus whatever probability you find for that Z-score, which I think in this case, this would be easier to find because again, you're just finding everything to the left of the Z-score and then subtracting 1 from it. To me, that's easier. But if this is easier for you to understand, do it. No harm, no foul, okay? But in this case, all you have to do is find the Z-score, again, 0.0764, and then you just take the inverse of that, which is 1 minus the probability, right? Because this goes from greater than to less than, so it's just the opposite. We get the same exact value. Look at that, look how that works, right? 92.4%. Again, we can use either table, whichever is easiest for you to understand, but we have to make sure we use it correctly. We have another way to use these Z-scores, and it's what's called the inverse normal, okay? And so what the inverse normal is we can find various normal percentiles, right? The 5th, the 10th, 25th, etc. Meaning that we can find the X for a given area just by turning the standardized formula around. All right, so we know the standardized formula, the X value minus the mean divided by the standard deviation. And this works for not just X, but this can work for standard deviation. This can work for mean. You just have to use this formula here and you can solve for it algebraically, right? We all know how to solve functions algebraically, I hope. But in this case, right, we can move this stuff around and we can get X equal to the mean plus the z-score times the standard deviation, right? That's how we can find the x value. So example, for the same exact exam, right? Mean is 75, standard deviation is 7. I want to take, or let's say I decided that for this exam, I wasn't happy with some of the scores, and I wanted to take any student that scored below the 10th percentile, and I'm going to make them retake the exam. I don't think I'll do that. This is for an example, okay? Exam score is normal, 75, 7. What is the score? So we're basically asking, what's the x value? What's the score that would require a student to retake the exam, right? So that means the area is 10% under the curve. What's the probability that the x is less than x? That's what that's saying. So what's this x value here? That's what we're trying to find. Again, we have to approximate the z-score, so we have to find our 10% under the curve. You know that it's going to be probably a negative z value just because of it's in the 10th percentile, it's to the left of the mean, okay? The z-score for the 10th percentile is around negative 1.28. Again, this is for quick reference. If you guys are like, oh, I don't know the z-score for the 10th percentile, it's this. It's always going to be this, okay? That's just a good quick reference for you. Again, using Excel or the Appendix C. You can use either or, but I would prefer to use the appendix. Again, we can sub in the information we know, right? So we know the z-score, we know our mean and our standard deviation. We're trying to solve for x. So if we move it around, we can get x equal to 75 minus 1.28 times 7. And we can get 66.04. So, and you can round down because it's 0.04. So that means if you scored a 66 or worse, you have to retake the exam. Okay? That's all that this is saying, right? That's all the inverse normal is, right? Instead of trying to find the z-score, we can now find the x value, or we can find the mean, or we can find the standard deviation, right? They'll give us the mean, or the x value, the mean, and the z-score, and we need to find the standard deviation. Well, we can do that. It's you just have to plug and play, right? If we don't have this, we can just solve for it, okay? Algebraically, of course. So anyway, that's just an example that we can use. All right, guys, we're zooming through this, and this is the last thing we're going to talk about before I'll let you guys go, okay? And it's what's called the normal approximations to the binomial. So in a binomial distribution, depending on certain factors, we can give it some normal approximations, right? And again, we've seen binomial probabilities. It can be difficult to calculate when n is large, right? That's that really nasty looking formula that we looked at earlier with all the factorials and all that stuff. It can take a long time to calculate. And so if it meets a certain criteria, we can then apply normal approximations to it, and then we can just, use the tables that we're already given, find the z-scores and all that, and then we're just sitting pretty, okay? So kind of the logic is like, as n increases, the discrete binomial bars become more like a smooth, continuous normal curve, right? So as n gets larger, you kind of see more of a continuous flow to it and a bell-shaped curve to it. It's easier to visualize a smooth bell-shaped curve overlaid on the bars of the discrete or the binomial distribution, okay? And so there's two rules. In order to use normal approximations on the binomial, there's two rules that it has to meet in order to do it, okay? And the first rule is that the number of times you take the binomial, or the Bernoulli experiment in this case, because that's all the binomial distribution is, right? It's just a Bernoulli experiment repeated a certain number of times. All it is you have to make sure that the number of times you did the sample, or the number of times you did the experiment times the chance of success is greater than or equal to 10, right? As long as this is greater than or equal to 10, you've met the first criteria. The second criteria is the number of times you completed the experiment times the chance of failure is also greater than 10, right? So we have to make sure that the number of times you completed times the chance of success is greater than 10, but we also have to make sure that the chance of failure is also greater than 10. If it meets these two criteria, we can then apply normal approximations to that binomial distribution, all right? And again, I just put these here. This is just a friendly reminder for you guys. Sigma is just the square root of the variance, and this is the variance, and the mean of a binomial distribution is the same thing as this. n times the chance of chance of success. Okay, that's all that this is saying. So step by step. I don't have an example for you. There's an example in this book here that I'd actually like to let you guys look at, and we'll give that to you so you guys can have kind of a visual of the step-by-step, or kind of the logic thought process behind some of the steps. But in general, this is kind of the step-by-step how-to of a normal approximation to the binomial function, right? So first thing we want to check, does it meet the two requirements for normal approximation? Are both instances greater than 10? If they are, we can move to step 2, right? And we have to find the mean and standard deviation of our binomial, right? Sometimes it's given, sometimes it's not. We have to find it, right? So it's just n times the chance of success. This one's the square root of the variance, n times the chance of success times the chance of failure, okay? Once we find that, we can then standardize our variable, right? We know standardizing variables is just our z-score, okay, with our desired x value. And then we can just use the appendix C to find our area under the curve, right? And then use the appropriate method for solving your normal approximation. We've done plenty of examples where we can find that and find the value accordingly, okay? So this is the general version. There is an example in your book that we'll pass out that we'll give you if you don't have the textbook, and you can kind of look at that as we do some of these problems, okay? So that's the end of this video. I hope you enjoyed it. I know it was fast. I know you guys want to get out of here. But I will say it is a class. We have to do some of these problems because if you sit here and listen to me talk for a whole lot, you're not learning anything. So we gotta give you some examples to practice, okay? So there's 6 problems. I know it's quite a lot more than what you're normally given, but I'll assign this as homework and you can bring it in next Monday. I like that. Okay, so enjoy your week. We will get those tests graded for you and get it back to you quick, and look forward to another video next Monday. See you guys.